Okay guys, problem number 1, electrostatics. Okay, so here we have a scenario there. Okay, two identical spheres A and B carrying charges 5 microcoulomb and negative 10 microcoulombs respectively, are separated by distance 30 millimeters. P is a point located at a distance of 15 millimeters from sphere B as shown below. Okay, so here is our point of interest. Okay, so we are standing here and then here are the charges. So we want to know how much of the electric field are we going to experience and what is the direction of that electric field. Okay, so now the spheres A and B are allowed to touch each other and then return to their original positions. Okay, okay, so now these two spheres are allowed to touch each other and then return to their original position. Okay, you will remember from the previous lesson that we did on electrostatics, whereby two spheres, they were in contact with each other, and then when they were separated, they shared a charge into half. Okay, so now that's what we're going to do here. Okay, so now okay, so now these questions, they follow from this statement after these two charges were brought closer together and then separated. Okay, so now 7.2.1, define electric field at the point inwards. Okay, so we will be expected to define electric field. Okay, so what is electric field? So electric field at the point is electrostatic force let me do this force, I want it outside, is electrostatic force experienced per unit positive charge, Okay, electric field at a point is a force experienced per unit positive charge. Okay, so now you must also put that electrostatic in brackets. Okay, because this is the kind of force that is being experienced per unit positive charge. Okay, and you can expand this and say per unit positive test charge. Okay, per unit positive test charge. Okay, per unit positive test charge. Okay, so forgive my handwriting. This app, it is not flawless, it is not meant for writing. Okay, so I hope you can see. So a 7.2.2 7.2.2, they say that draw an electric field pattern between A and B after touching. So they are explicit with their question, after touching. So now when these two charges touch, what is going to happen? What is the charge between them after they touch? You'll notice that this one is positive and this one is negative, and this one is twice this one. So let's see what will happen. Let's see what will happen. So Q1 plus Q2 divided by 2 is equals to the final charge. Okay, so Q1 is 5. It's 5, positive 5. So we have 5 plus into minus 10 divided by 2. So let's see what is the charge on each sphere after contact. 5 minus 10 divided by 2. So we have a charge of negative 2.5 on each sphere, microcoulomb. Okay, so this is the charge on each sphere, meaning now we have negative charges now. Okay, so now meaning we're going to have negative and negative. Okay, so now electric field pattern between A and B after touching. So this is going to be something like that. Okay, remember their magnitude is the same now, so also the number of field lines must be the same. Okay, so and remember that for negative the field lines go inwards like this. Okay, now this is A, this is B. Okay, so this is your answer. You see 3 marks. So 1 mark, I guess it will be for you to determine whether they will be positive or negative. Okay, but yeah, or for the shape being like this and then the field lines going inwards. Okay, so 7.2.3. So 7.2.3, calculate the magnitude of the net electric field at point P. Okay, so now all of them are what? They are negative now. Okay, so now we follow this statement, because this statement says that sphere A and sphere B are allowed to touch each other and then return to their original positions. Okay, so now these charges, they no longer work. So what are we going to do here? This one here, this one was not required here. Okay, so we are going to repeat this step here. Okay, so that step is charge Q1 plus Q2 divided by 2 will give us 5 plus into minus 10 divided by 2 is equals to negative 2.5 micro coulomb. Okay, so this is the charge on each sphere. Okay, so now we know that here we have a negative charge, here we have a negative charge, and then here this is P. Okay, so we know that when I'm standing here at P, this one, the field line goes away from P, goes to the left, and also this one, the field line goes away from P. So if I block this one and then I only focus on this one and this one, and the field line for this one goes away from P, also this one. So now the field lines, they go to the left, all of them. So the electric field, the net electric field here is going to go to the left. So I have something like this, you see. So the net electric field will go to the left, you see. So here I have EA and EB, you see. So and then this is E net. So and then now I can choose my direction, because all of them, they're going to the left. I can say choose to the left as positive. Okay, choose left direction as positive. Okay, so now I'm going to calculate the magnitudes of each of each field. Okay, so now EA, notice that the electric field is not going to be the same, although the magnitude of the charges are the same. Okay, so because of the distance between the P and A and P and B, they are not the same. Okay, so here okay, between A and P we have 30 plus 15 milliliters, so we have 45 millimeters, sorry, not milliliters, millimeters. Okay, 45 millimeters. Okay, so electric field due to A over R squared, 9 times 10 to the power 9, here 2.5 microcoulomb divided by 45 millimeters. Okay, so milli okay, okay, so milli is times 10 to the power minus 3. Okay, so let's check again. Is it? Yes, it's micrometers. Okay, so now 9 times 10 to the power 9 multiplied by 2.5 times 10 to the power minus 6 divided by 45 times 10 to the power minus 3. Okay, all squared. So I have 11.11 times 10 to the power 6 newtons per coulomb. Okay, and then EB, so KQB divided by R squared. So 9 times 10 to the power 9 multiplied by QB, 2.5 times 10 to the power minus 6 divided by 15 millimeters. Okay, 15 times 10 to the power minus 3 all squared. .5 minus 6, 15. Okay, so now I have what? I have 100 times 10 to the power 6 newton per coulomb. Okay, so since now they all going to the left, okay, so they're all going to the left, and then I say left is positive, so E net is going to be EA plus EB. Okay, so I'm going to add these values together. I have 11.11 times 10 to the power 6 plus 100 times 10 to the power 6. So how much do I have? I have 111.11 times 10 to the power 6 newton per coulomb. Okay, so now this is our final answer. Okay, let's try another problem. Okay, so we are at another problem number 2. Two charged spheres R and S are both stationary on a smooth insulated surface inclined at an angle 25 degrees to the horizontal. Sphere S of mass 0.01 kg and carrying charge of -6 times 10 to the power minus 9 is connected to a 0.03 meter long light in an extensible string attached to point P at the point of incline. Okay, sphere R carrying a charge of 5 nano coulomb is held at such that the distance between the centers of the spheres is R, as shown in the diagram below. Ignore the effects of friction. We have a beautiful scenario there. Okay, so here we have two charges there. Okay, so this one is experiencing tension T here. Okay, and what else? It also experiences gravitational force parallel, this one, and also it experiences electrostatic force as well. Okay, so very interesting stuff. Okay, so now notice that even in electrostatics we can include tension, we can include gravitational force, because at the end of the day they are forces. Okay, so now sphere R exerts an electrostatic force of magnitude 1.2 times 10 to the power negative 3 on sphere S. Okay, so now we have R there. Calculate the distance R between the spheres. Okay, so we can do this one first. Okay, you can say F is equals to K Q1 Q2 divided by R squared. This is Coulomb's law. Okay, Coulomb's law. Okay, this is Coulomb's law. So now what do we have? We have F, we have and everything here. What we don't have is R. Okay, so now I'm going to rearrange this and make R subject of the formula. So meaning R is going to be the square root of K Q1 Q2 divided by F. Okay, so now the square root of K is 9 times 10 to the power 9 multiplied by QR 5 nanocoulomb, the other one is 6. Okay, 5 times 10 minus 9 times 6 times 10 minus 9. Okay, divided by the force. Okay, how much is the force? The force is 1.2 millinewtons. 1.2 times 10 minus 3 newtons. Okay, so now remember this is a square root. Okay, so proceed to press square root 9 times 10 to the power 9 multiplied by 5 times 10 to the power 9 multiplied by 6 times 10 to the power negative 9. Okay, divided by 1.2 times 10 to the power negative 3. Okay, let's see. So now we can see that R is equals to 15 times 10 to the power minus 3 meters. Okay, so which is 15 millimeters. You see? So now let's go ahead and draw a label free body diagram for sphere S. Okay, sphere S. Here's sphere S. Okay, so now sphere S. So we know that on an incline, what do we have? We have a gravitational force parallel. Okay, but then we know that it is due to this force Fg, gravitational force, and then there is tension. There's tension. What else? there's also electrostatic force. So this is negative and this is positive, so it's experiencing a attractive force down the incline. Okay, attractive force down the incline. Okay, and then let me write this very nice. Let me write this very nice. Okay, yeah. Okay, so this is Fe for electrostatic force. Again, what we have normal force, Fn, okay, or just N. So it's 4 marks. 4 marks here. 1, 2, 3, 4. Okay. So now let's go to 7.4. 7.4, calculate the tension in the string. Okay, so we have Fe. Okay, so now before we can do anything, we start by saying F net is equals to what? Remember, this is stationary. Okay, so it is in mechanical equilibrium, so F net is equals to ma. Okay, n is equals to 0. All right, so now, and we know that F net is equals to we can choose direction and say down the incline is what, or we can say up the incline is positive and say T minus gravitational force parallel minus the electrostatic force. Okay, so now F net is equals to 0. We don't have T. What is Fg parallel? Is mg sine theta minus Fe. Okay, so Fe, we have Fe is 1.2 times 10 to the power negative 3 newtons. Okay, so, and what is the mass and the angle there? The mass is 0.01 kg. Okay, so here 0.01 kg times 9.8, the sine of what is it, 25 or 25 degrees, 25 degrees minus 1.2 times 10 to the power minus 3 newtons. Okay, T is equal T minus that. Okay, so that is our equation. Okay, 0.01 multiplied by 9.8 sine 25 minus 1.2 times 10 to the power negative 3. So here I have 0 is equals to T minus 0.0402. Okay, so let me take this to the other side. So now I can see that my tension is 0. So let me write it in scientific notation. Okay, 0.04022. So in scientific notation is 40.22 times 10 to the power negative 3 newtons. Up the incline. Okay, up the incline. So this is my tension force now. So now 7.4.2, calculate net electric field at point P. At point P. Okay, where is point P? So now you notice that this one is negative, right? This one is negative and this one is positive. Okay, so with respect to P, the field lines this side, they go inwards. Okay, they go inwards, and then here they go outward. So this one they go up the incline, this one down the incline. Okay, and we said up the incline is positive, okay, and down the incline is negative. Okay, we can also write the direction again for the electric field. Up the incline is positive. Okay, or just do this. Okay, so now already we know that our E net, it is going to be ER minus ES. Okay, we know that this is the general equation for of electric field, but then now we have ER plus into negative ES. Okay, go back again and see. Yes, ES goes inwards, goes down, and then ER goes up. Okay, so now meaning here I have ER minus ES. Okay, so let me go ahead and calculate that. Okay, so first of all I have to calculate ER. So ER is given by KQR divided by R squared, equals to, what is the distance between P and R? Okay, so this P and is this R that we calculated plus 0.03. How much is R? Is 0.015 plus 0.03. So 0.045 distance. Okay, so 9 times 10 to the power 9, 0.045 all squared. Okay, and then what is the charge? The charge of R, 5 nanocoulombs. Okay, 5 nanocoulombs. Okay, the other one, let me write the other one here. ES KQS divided by R squared, 9 times 10 to the power 9, and 6 nanocoulombs divided by 0.03. Okay, I think that's that. Yeah, okay, yeah. Okay, so now let's calculate our magnitudes now. 9 times 10 to the power 9, 5 times 10 to the power 9 divided by 0.045 all squared. So I have 2.22 times 10 to the power 22 Newton per Coulomb. And then here at the bottom, I have 6 times 10 to the power positive 22 Newton per Coulomb. Okay, and then E net is equals to ER minus ES, right, is what we have deduced there. Okay, so where is ER? It's 2.22 times 10 to the power 22 minus 6 times 10 to the power 22. Okay, so 2.22 minus 6, I have negative 3.78 times 10 to the power 22. So remember, I said up the incline is positive, therefore now E net is equals to 3.78 times 10 to the power 22 down the incline, or away from P. Okay, or away from P. Okay, so, or we can say southwest. Okay, so now this is the answer that you get for that. Okay, okay, so here's another problem. Okay, but this one, I think it requires its own video as well. Okay,